So we'll talk about nanofabrication. There's something that you must have already seen, you must have had question, how we make things small, how do you, what is a mask and all that thing. So we'll start with basic semiconductor materials, especially silicon. And why we do that? Because a lot of development in nanofabrication has come from semiconductor industry, where we're still trying to make devices smaller and smaller. So that push to make things smaller and smaller has been a cornerstone of semiconductor device industry, not just USA, all over the world. And what it has done is not just created new tools for fabricating small things, but also tools to uh, have metrology, measuring those processes and those outcomes. So we'll go over some basic concepts that are related to first semiconductor materials and then simple fabrication steps and how do we go from a silicon substrate to make a device on that. So semiconductor materials are materials which are neither good insulators nor good conductors. So they fall somewhere in between. If you look at the periodic table, we call that group 4 elements. Within group 4, silicon, germanium, these are the topmost materials which are used to make our devices. Germanium used to be used a lot, but then silicon has become the major player, silicon material. And we'll see why is that. Now, it's not group 4 only, we use combination of group 3 and group 5 also. We use compounds of those things as well. In that case, we call them compound semiconductors. The simple concept here to understand is group 4 has 4 electrons in the outermost shell. This may be fundamental chemistry for many of you, but you know, that's the idea that we can build up on what you know already. Now, the outermost shell is half empty. So when you would have silicon in a crystal, silicon will make covalent bonds with 4 other silicons, so they all will share their electrons. So essentially, the outermost shell gets filled up. It's a simple way of saying that, but in reality, it's a little bit more complex than that. But we say, okay, the outermost shell gets satisfied. All 8 positions get filled up. Now, group 3 has 3 electrons in the outermost shell. Group 5 has 5 in the outermost shell. When we combine them together, we get the same results. Electrons come from one side, 3 come from the other side. The outermost shell is filled with 8 of those. We do the same thing if we mix group 2 and group 6. That's also a combination we use to make semiconductor devices. Now, they all are not always used for electronic devices. Many of them are used for optical devices as well, right? What do you mean by optical devices? Can you give me an example of an optical device?
I'm not sure. I'm actually, just throwing a wild guess. One, would it be the filters on the glasses or fiber optic?
Devices. Give me an example of a simple semiconductor device that has to do something with light. Okay, give me a simple electronic device that has to do something with light.
The electron, I forgot the exact name, but the microscopes.
There's a light bulb in your room. Do you have a light bulb?
Yes.
That's an optical device. But what about an electronic optical device? Give me an example of that. Luis is laughing. Luis, do you know the answer? Right, optical device. A diode that does something with light.
The LED.
LED. What does D stand for in there?
Diode.
A diode, yes, sir. Light LEDs, light emitting diodes, right? These are semiconductor devices, but they are not electronic devices. They are what? Optical devices, right? That's a very simple example. We have so many optical semiconductor devices around us. All your cell phones have those cameras. Cameras are doing what? Capturing light. They are, what do we call them? Light capturing devices. And we have many of those. They, you have too many of those photodiodes, bring them together becomes a camera because now it can capture all those pixels. Right now, we are communicating through optical semiconductor devices, right? So they're not just group 4, so they may be combination of group 3 and 5. But now something to learn from here that they have become so small, smaller and smaller, right? Now they can be integrated with so many other things on one chip. That's what has happened because we are making them too small. Now, how is a semiconductor material special? Because we use them in crystalline structure. And when you say crystalline structure, we are basically talking about uh, just like diamond, where atoms are placed in very precise order. And if you talk about silicon, crystalline silicon, yes, we find silicon in non-crystalline structure as well, right? Which would be in the form of silicon dioxide or silica, basically sand. But we refine it. We refine it so much that we get a high quality, uh, very, very, very rich and with very small, uh, what do you call, if you make something very pure, it has no impurity. So on one side, our goal is to make it very pure. The other side is we want to get everything out and just have silicon atoms, for example, in there. There are other examples of semiconductors like we see here, but I will just stick to silicon because many of the processes are the same for others. Now, when you have this in crystalline structure, that's when we have a semiconductor material. And then we incorporate things into it. We'll talk about many of those today. Now, why silicon? I said there was germanium that was used, but silicon has become so important. Only reason is because we can have silicon dioxide out of it. Now, silicon dioxide, it's like glass, right? While silicon is conductor, semiconductor, silicon dioxide is a very good insulator. And when you're making devices, you want to have some areas which are electrically conductive, but you really want some areas which are electrically insulated. So that's why we use silicon only because we can make a good silicon dioxide. Can somebody tell me what is oxide or oxidation? It happens everywhere, all the time. Can you give me example of oxidation? When you uh, leave your uh, bike out in rain or you live close to the sea, what happens to the metallic parts?
Rust.
Rust. Rust is oxidation. That's as simple as that. So every material has some form of oxidation going on. When you cut your apple, why does it go brown?
Oxidizing with the
Oxidation, right? So now silicon, when you make pure silicon, again, there is some oxidation, but we are not just depending on oxidation from the ambient. We ourselves oxidize those silicon wafers. We oxidize because we want to grow a thin layer that has insulating properties. Now, when we are talking about silicon, we are talking about semiconductor. Why do we need an insulator? We'll see that very soon. Some examples are also given here, but they would not mean much to you at this stage because we haven't talked about it. So the example that are written here is that good oxidize can be used as a diffusion mask as a dielectric for adhesion, for surface passivation. It's okay. If it doesn't make sense right now, that's fine. But our goal is to look at those things. Now, there's another word used here. It has a good crystal quality.
Sir,
Yeah,
what does it means like dense pinhole free dielectric?
I'll show. I will talk about that. So there's simply what it means. A dielectric in silicon industry, when you're making devices, when you put insulator at a surface, you call it dielectric, a dielectric material. If you remember capacitor, that's where we use dielectric. So that inner material is basically an insulator and you have two electrodes. So we call it dielectric. Pinhole is a quality where if you put a very thin layer down, a hole in that layer is what we call pinhole. That we don't want pinholes into our devices because they would cause electrical short. So, but we'll see where it becomes important.
So the silicon can work similar to the PDMS, for example?
No, PDMS is a polymer. Silicon is a hard material. Polymer means it's a soft material. It's a kind of a rubbery thing. But silicon is a hard material. It's
Okay, thank you.
Yeah, it's a solid. All right, so now we talk about crystal. This has to, the crystal, the basic quality of a crystal is that it has periodic repetition of atoms. So periodic arrangement of atoms. And we call that periodic arrangement as a lattice. And for this periodic arrangement, if it happens over a long period, then we call it to be a crystal. We call it a crystalline material if that periodic arrangement occurs for a long period of time, on a larger range. And the opposite of crystalline material is amorphous material, a material which has no atomic order in it. The example, if we are talking about diamond, what is diamond made up of? Can somebody tell me, like transparent, shiny glass diamond, what is it made up of?
Pressurized carbon.
Carbon, right? It's just carbon. Now, if you pick up your graphite pencil, what is the black thing made up of? The graphite?
Carbon.
It's carbon as well, right? So you go make your barbecue, you use coal, again, carbon. The difference is the graphite or your coal is amorphous carbon, no order to it, no order to the how carbon is attached to other carbon. But diamond is a crystalline material. Carbon is very precisely attached to other carbon atoms. And then there's third kind is, so these are basically three types of solids. So the third type is polycrystalline, where you might have some crystalline structure and then there's no order, and then you may have another area where you have crystalline structure. An example of that is graphite pencil. So the graphite has some layers of carbon which is coming in very precise order, and then there is no order, and then there's more carbon. But essentially, why it matters, because that's the only way we can use it into make devices. So there's steps involved where you have raw silicon dioxide from sand, you would purify it, and then what you would get is what we call them ingots of silicon, high purity silicon. Basically, they are made in a cylindrical shape, and then we chop them off into smaller pieces. When you chop them off, we get this thing on right hand side. We call them wafers. So here is an example of some wafers I have. Let me switch off the background, because if there's background, then Zoom does not show all the details of things. All right, so this is what we call a silicon wafer. This is unpolished. I have the polished one also. But if you look at it, this is about half a millimeter thick, half a millimeter. How many micrometer is that? Half a millimeter is 500 micrometer. You'll be doing this conversion when you get to the exam. So, and this is crystalline material. They make it too many, so they are cheap. So this is a $20 thing. One wafer is $20. I have a bunch of those from my PhD days lying around because sentimental value. I spent too much time working on these. They haven't done anything. Now that was an example. That was an unpolished wafer. I have some polished wafers also, but I have put gold on those things, pure gold. But if you think about it, this is basically a silicon wafer that has been chopped off from this big ingot that I'm showing. And then once you chop it off, you make devices on top of that. So this has gold on it, but I don't know, in the shade, if you can see some features on it, some dots, repetitive dots. These are, you can see a zoom window on this. Can you see some features which are built? These are some devices that I made. But this is, by the way, this is pure gold on it. I don't know how much. Maybe some nanograms gold on it, but it is made into atomic layers, very maybe few atom thick. We don't keep them like this. They're supposed to be in very clean environment, but these are wafers, old wafers, dummy wafers. So you get the wafers, and then we start building our chips or our things on top of that. That's something we are getting into. So you get big things, big cylinders, you saw them off with the wire saw, you polish them, you do everything. And then what we get is, we have the wafers. Basically, I skipped through all these steps. You melt it, you saw them, chop them into smaller pieces, you polish them, you etch them, and what you get is, you get wafers, you test them, and then they come to us for industry to work on. Now, what do we do? When you get the wafer, what are the things we do with these wafers? That's the question. That's what we will do. All right, so now another thing before we get into what we do, every wafer has some specific properties. They come in standard sizes, all the way from 2-inch to 16 inches. Industry, they use 16-inch wafers, and they don't use single wafer like I was showing. They use stack of wafers. It's called pod. So it has 20 wafers, for example. They go from one process to the other process. And they have specific doping, which we may have doped it while we are making the silicon cylinder. So that's what would make it N-type or P-type. You know N-type and P-type. We'll talk a little bit in detail later on that how do we make a wafer or silicon N-type or P-type. Now you got the wafers, what processing do we do? Let me take a step back and let's just think about that. How many of you have made a printed circuit board or designed a PCB? You guys know what is a PCB?
I did one, but being quite honest, I was handheld through the entire process it was back in 8th grade.
That's perfectly fine. Let me ask something. How many of you have seen PCBs? Okay, open any uh, electronic or electrical system, you will see there will be PCB in everything. A simple thing, maybe open your remote control, you will see a PCB in there. Everything has a PCB, printed circuit board. It's a piece of plastic which has devices, components soldered with each other. And there are metal lines that run. Now, somebody designs that. Here it is. Dan is showing us a PCB. Fantastic. Now, then let me show it to me again. Let me take a picture of it. Bring it close to the camera. What I'll do is let's see if I can print the picture and take a screenshot and share that screenshot with everybody else. All right. Thank you, Matt. Now, there are many interesting things in this. Let's see if I can, how can I share that? All right, you can see Dan's PCB now. So there are a few things. So there's these white lines running around, right? And then you see there are some kind of bubbly things at the end of those lines. And then you see there is this brownish background on which everything is made. So basically these white lines are connections. Those are leads. And on the other side of the PCB would be the component that's been put down and its leg has come out to the other side and they're done soldered, those things there. Yeah, Dan is showing another PCB, the other side where the components are. All right, very good. So you can see there are LEDs at the bottom. Now, how does the process start? Somebody thought about, okay, then what does this thing do, by the way?
So what he used to do, it's we programmed the microcontroller to light up the LEDs one by one, and then it was just a sequence, just one by one.
So Dan thought about, I want to make a device in which I want to use a microcontroller to light up devices one by one. All right, that's where it started. And then he said, okay, what would be the components of that circuit? He would probably sit down and on the paper, he drew the circuit and he looked up maybe online, looked up a book, what resistance has to be used, what capacitor needs to be used, what would be the connection of the lines and all that stuff, all the good stuff on paper. All right, paper. Now, from paper, how do I make the circuit? So he had to sit down and use a software, maybe PSpice, to simulate that circuit to see if it worked, right? And now came the time, okay, now I have to lay it out so I can build that circuit. Now, think about it, from paper, it went into simulation on computer, from simulation, it went into an actual layout of the circuit. And from that actual laying out, the file went to a company in China who made that PCB and shipped it. Or maybe you made it yourself, right? Yeah, we can make it.
Yeah, I did it old school. I actually had to iron it.
Oh, you did?
Once I designed the circuit, I printed in with a laser printer, and I bought the copper thing, and then I had to iron it on top of it until it was fully stuck in it, and then I submerged it into acid. And then
let me stop you there. Let me stop there. So you made the circuit and then you transferred that circuit by ironing to the PCB itself, right? So transferring that is keyword here, that you made the design and then you had to transfer on the actual PCB So you could then, so now you put the whole thing into acid. And in acid, what does acid do, by the way, guys? Just in big life, if you if I
Burn.
throw acid on my floor, what happens?
It'll burn.
Burn is on us. It burns us.
Dissolve.
But when I put it on the floor, maybe on my tile or on my flooring, what does it do? In most fundamental terms, it reacts, right? It does the chemical reaction, right? That's what it does. Yeah, the result of chemical reaction is it results into a byproduct, and during the process, it's an exothermal reaction, heat, which we say burn. But I want you to remember this exercise, what we have just done, because in silicon processing, in making your diodes, photodiodes, resistances, LEDs, we do all these steps, but we do it at smaller scale. We use acids, we use transferring of pattern from a computer file onto actual silicon wafer. Dan, sorry, I cut you off. Let's come back to where you said you ironed it and what you did it.
Yeah, after I ironed it, I submerged it into acid. That way, the acid will remove.
Etch. Etch is the right word. The acid would etch away. It's etching, right?
Yeah, and that's what forms the white pads, because it peels off the copper from it, and that's what the acid's for.
Right. So there was a reaction between acid and copper. So where the copper was exposed, that got etched away, and where you had put that iron, the circuit design, it was basically a protective layer that you have put down. The acid did not etch that protective layer. It just etched wherever the copper was exposed, right?
That's correct.
You have just used a mask. That's the word, a mask, to cover the area you wanted to stay, and that's what shows at the white lines on your PCB. Can you show it again? So the white lines was where you had ironed the protective layer, right? And the brownish places, so that's copper, but the whole thing was covered with copper before, but then he made the pattern, used a mask to cover the areas, and when he dipped the whole thing in acid, the acid etched away the exposed part, but it could not reach the covered part, the mask part, and that stayed. And that's what helped you make your circuit.
That actually helps explain what happened. I was going to ask, back when I did it back in 8th grade, like I said, I was handheld through it. We drew on top of a film with marker. And then the marker is what ended up being the circuitry. And you just saying that explains exactly what happened.
Let me break it down. So the marker basically acted as a protective layer from your acid to reach below. Everything had get etched away, but your masked region did not get etched away. This is the most fundamental feature of silicon processing. This is the most fundamental feature of the whole Intel's, AMD's, or whatever big semiconductor companies are doing, whatever. That's the most fundamental step. Now, but it's done at a smaller scale. Right? Now, let me give you a big list, and then we'll get into simple, into one of the fundamental process. So there are a bunch of processes we do. We have a silicon wafer, like I showed you. We have to transfer a pattern. Now, who makes this pattern for this gazillions of transistors on a chip surface? Who are those engineers? What do we call those engineers? What kind of engineers are those?
Geniuses.
Say it again?
Geniuses.
Genius? No, man, it's not rocket science. It's just called VLSI engineers. VLSI. Have you heard the word VLSI? this is another professor. She teaches Introduction to VLSI. VLSI, Very Large Scale Integration. Right, Cecilia? With me? You have heard the word VLSI?
Yeah, I've heard that there's a class. I actually want to take it next semester.
Fantastic. So before you learn how to make circuit, I'm going to teach you, once they make a circuit design on their computer, how do you transfer that onto the chips to make that circuit, right? So both sides have to work very close to each other. So that's the pattern transfer. They make a design, they make multiple levels of circuit in VLSI, and then we transfer that on the surface of a chip. There's another, I'll jump through, not all of them, I'll jump through pattern transfer. We would do maybe ion implantation. So we would dope certain areas. If you want to make a diode, P-type and N-type. So I would put P-type material at some place, and then I'll cover that. I'll make another window next to it. I'll put N-type material next to it. P and N next to each other. What is it, Orlando?
What was that?
If you put P-type material and N-type material next to each other, what kind of device is that?
I'm not sure.
Okay. P and N. P-N junction. What is that device called?
A diode.
A diode.
Oh, wait.
Yeah.
Are used to make transistors, or right?
So you used to make transistors. Say it again.
Are diodes used to make transistors, or?
So now, fantastic. So I was just saying, I put P-type and N-type doping. That's a diode. But if I put P, N, and another P, that would become a transistor, right? Two diode back to back, you bring them together, becomes a transistor. So that's ion implantation, probably, which we would do to make one area P-type, another area N-type. Just stay with me. We'll see how it happens and where does it happen. I would maybe do some etching, like we were talking about acid etching, to remove some material from some places. We may want to deposit some material some places, like copper material, so we can make connection with the outside world, right? So, but all of these things go into silicon processing. The most fundamental feature in device fabrication is what we call as photolithography. This is a big word. It's a very important word. Photolithography, we also call it optical lithography. What is lithography? Have you guys used a stamp ever? Stamp? Right? You know, professional engineer, you have a stamp. You have to stamp something, right? You go to invoicing, they would say paid. They put a stamp of paid. They give you the receipt. It says paid. Stamps. You're becoming, not using too many stamps these days, but stamp is a thing. What happens in a stamp is you dip it somewhere into ink and then you put it and the ink gets transferred. That's lithography. They used to make newspapers. Do we get newspaper these days? Or we get all our information from CNN or wherever you go, Fox, I don't know. So, but there used to be a thing called newspaper. Have you guys seen a newspaper ever? Maybe
Yes.
some of you have.
Black Friday ads.
Friday ads, right? Or coupons. Coupons. We need coupons. How do they make newspaper? It's a blank page, and they have these big plates that are rotating. The thing is rotating. A page comes, touches it, throws it out. So this thing is rotating in circle, and the straight paper comes and touches, throws it out. They show it in the movies. That's called lithography. Basically, transferring a pattern is the process called lithography. Now, but I'm saying photolithography. So using light. using optical ways to transfer a pattern. Now I have a big picture here, which I'm going to make bigger, and then we're gonna go through this. We're gonna go through it in much detail, but I just used a stupid animation to make it large. All right, VLSI person made the design from their mind, put it on computer, the design layout is there. Somebody has to take that design and transfer onto the surface of this silicon chip, this wafer that I showed you. How is that going to happen? We make a thing, what we call as mask. Mask is a tile. You know, tile is a squarish thing. Tile made up of glass. It has a coating on it on one side. The coating is of a material which is opaque to light. If it's opaque to light, if you put it under light, you would see a shadow on the other side. That's what it means, opaque. But the design, the layout, we transfer that. Maybe we use laser. We write those small lines and areas and all those things on that opaque material. Now, if you put that mask under the light, you will see there will be a design that will be reflected on the surface below, right? Like if you put a light and people make these things like you see a duck, you see an elephant with the hand, and you see the shadow on the wall. So similar way, on the other side of the mask, when they put the features and you shine the light, what is shown here, you have a light coming from the top. I'm going to work on the slide to show you. Okay, so the light, from here, the light is coming down. And you have this thing, what is called mask or reticle. It's a similar thing, but you see a squarish plate, which has these lines, which are made to be look transparent. It's whole grain, but some areas which are made transparent. Light will go only through that transparent region and shine on the other side. What is on the other side? On the other side is my silicon wafer. Now, what I've done on my silicon wafer is I would coat the silicon wafer with a photosensitive thin layer of material, photosensitive layer of material. When I say photosensitive, which means that if light strikes on that material, wherever it strikes, that material changes chemical properties. Hector, is it going too fast or too slow?
No, I'm actually trying to like visualize the picture. That's why I'm just staring at it super close. I'm trying to visualize the idea.
Yeah, I'll go through a few examples of this process with you. But there are simple idea is that I take my silicon wafer, I'll coat it with a layer of a layer of a material that's photosensitive. And now I shine the light through a mask, and that mask makes sure the line strikes only at certain parts of my wafer. And wherever it strikes, the material, the coating that I had will undergo some chemical changes. And now if I dip that wafer into a washing material, only the part that was exposed to UV light, that will get washed away. If that gets washed away, I'm gonna jump through few things. I will get this kind of design transferred, the pattern transferred over my chip. The gray thing is, so it's showing a side view, it's a 2D, I'll show you 3D. So this is the process of transferring a pattern using optical lithography. Why it's optical? Because the light source is an optical light source. It's UV light most normally. Have you guys ever used a camera they used to have which used to get a roll in it? How many have seen that roll camera?
The ones that use film?
Film, yes, the one they used to use film, right? Some people still use that who are 35 right? It used to have 36 exposures. You could stretch it and get 37 exposure. That camera, Cecilia, do you know what I'm talking about?
Yes.
All right. They used to be, when you go to Walmart, they have this photo section, right? And nowadays it's just you take your flash drive, USB, whatever, and they print your digital print. But it used to be that you had to take that roll to them, and then they would make negative out of it, and then they would use negative to make your positive. What was that roll? What was that thing called negative? That was nothing but a strip of plastic which was coated with photosensitive material. Are you with me on this?
Yes.
So the camera, when they would click the camera, what would happen? The shutter would open, the light goes inside the camera, strikes the film reel, and the reel is coated with photosensitive material like I'm talking about here, and that gets exposed. Now, they would take it into a dark room. They would take the reel out, dip it into what you call developer. Now, wherever the exposure light, dark light, color light, heavy light, that would get transferred into that reel, which was called negative. And then they would use negative. They would do the same thing, by the way, now. But now they would put the negative, which is now the mask. Think about it. They would shine the light through it, project it on your white paper, which was coated with photosensitive chemical. After exposure, they show it in movies, right? Dark room, red light, and people are taking pictures and hanging to dry. That's what we do in photolithography. It will become clear, the analogy will become clear. Just stay with me. Why I'm spending too much time on photolithography? Because photolithography is the mother of nanotechnology. It's the mother of how we can make things so small. So if you learn this, a lot of things become easy. What I just said, I've written it down. We make the circuit layout, and there may be multiple layers we design. So we have number of masks that go into it. And mask is nothing but a physical representation of the device features. Different areas will have different features. It's a glass plate which has now the pattern put on it like transparency. You guys know what a transparency is, right? A transparent thing, but now we put the laser printing at some places. And that's clear and opaque region, which is made of a chromium film. And that's the mask. Now on the wafer, we put the photosensitive material. We call that photosensitive material as photoresist. This word is going to come back over and over. So photoresist is nothing but that photosensitive material that we coat on the wafer. I would write it PR at later stages. You would see it written as PR. If you see PR, that does not mean green card. That does not mean permanent residence. It means photoresist here. You guys know what is PR? Yeah, immigrants. I'm an immigrant. I know. All right. So, yeah, don't forget to vote. Citizens need to vote. So we spread it, and then what we do. Here's a small animation I made. So you have wafer, silicon wafer. I'm just showing a cross section. We grow oxide on both sides. And then I coat it with positive photoresist. Now after coating, I can remove silicon dioxide from the other side, but what's important is I bring my mask down. Now this mask is showing golden region, which is opaque, and white region, which is transparent. I shine light. UV comes in. Now UV can go through only the transparent region and not the golden region, which is opaque for UV. The positive photoresist, which is exposed in that region, undergoes chemical changes, and hence I can remove it. I dip it in solution, that gets removed. Now I have transferred that pattern in photoresist. But photoresist is plastic type chemical that I've coated. I have to transfer that pattern in hard material, which is your oxide. So I do an etching step. There's a certain acid which etches only silicon dioxide and does not etch silicon. When I do that, I remove my photoresist. Voila. What do I get? I have my pattern transferred in hard material silicon dioxide. The whole wafer is covered everywhere. Only that window is open where I designed it to be open. Now I can dope P-type material through this window, and then I can repeat it and go next to it. And if I can make this P-type, then I can go to the next region, repeat the same thing here, and I can make an N-type pocket here. What would I get? A diode, right? This is the basis of integrated circuit, what I just showed you. All right, let's move on this concept and look at few more examples before we open for questions. So the steps are, we transfer the pattern. This text has become misaligned. So what are we doing? We have photoresist coating. When it's exposed to UV light, it undergoes chemical changes, which changes its solubility. So when I dip my wafer, so okay, what do we do? I put my wafer into lithography machine. I had the coating of photoresist. After I exposed it, I take my wafer, I dip it into a solution, a developer solution. So I dip it, wash it. Now the photoresist which was exposed will get washed away and leaves behind the pattern, just like the pattern I was showing you in gold. Now I will put it in another machine, and maybe I want to do etching, maybe I want to do doping, whatever I want to do. Now, how small of a feature can I make? That's what is called critical dimension, CD. So CD tells us how small of a feature can you make and repeat it over and over, because next step also, when you come, you have to make something else on it. We use UV light. We can also use electrons or X-rays also, but that's something will come later to that. They have different wavelengths, so wavelength has a major impact of how small can we make. Now here's a 3D view of what we have been talking about. We apply photoresist, and once we are done with the application, here comes the mask. Mask had this area which was opaque, and everything else was, maybe color code, and everything else was transparent, right? So when you use this to throw light, after we are done throwing light, what happened was In a positive photoresist, this region stayed and everything else got washed away. There is another kind of resist we use called negative resist, in which it's the opposite. Whatever gets exposed gets washed away. Whatever gets exposed stays, and whatever is not exposed gets washed away. Just a reverse. So here are the steps. We apply photoresist. If we had a feature from previous lithography step, we have to align our wafer, align our chip according to that. We expose it, we develop the photoresist, and we transfer the pattern, and then maybe we etch oxide, and that pattern gets transferred into the hard material. Questions? All right. Now, this is light. Light has its own problems. For example, if you think about it, when light enters from one medium to other medium, what happens to it?
Refracts.
Refracts, right? Changes angle, how it was going, right? That's first thing, one thing. What other things happen to light when it strikes a medium, different medium? Some of it can get reflected, turns back, right? What else happens to light?
Some of it can be absorbed.
Some of it can be absorbed, right? Some of it can be what you call refracted with R, refraction. Reflection, refraction, deflection, there is another one. We'll come to that. So
And
now,
it bounces off itself.
It bends. When it changes medium, the numerical aperture, not numerical aperture, there's an index of refraction that has different impact on light. There's another thing, light travels at waves, right? Now, when I have these small openings in the mask, some light will come from one opening, another light wave will come from another opening. Before the mask, it was all one wave. Now it would become two waves. When two waves are traveling next to each other, what happens at the intersection of two waves? Luis, are you with us? Hector, what happens to two waves that are traveling together at their intersection? What happens?
Mm,
I'm asking Hector.
I'm trying to think. If two intersect each other, or like if they go together, or
Yeah, if they are traveling together, what happens to where they intersect with each other, two waves, what happens there?
well, I mean, if it's light, wouldn't they change like their how do you say it? Like their wave would be like modified?
Wave would be modified. If they are both in phase, what happens to the resultant there? It amplifies. Do you know the concept of superimposition of waves? Constructive and destructive interference. If two waves are traveling in phase, what is the result? Overall result, they both get superimposed. The net result is the net wave is higher in amplitude. But if they are out of phase, they would have negative effect. They would cancel each other out. So there are,
like if they go together, the wave would amplify, but if they intersect, they cancel each other.
no, if they are in phase, if they are both in positive and negative going together, they will superimpose. But if one is going up, the other is going the opposite way, they would cancel each other out.
Oh, okay. Thank you.
Now, when I make a mask, there are so many openings. So when the light goes through, the light interacts with each other. Okay, if I cut through this science, the problem is there is what you call as Rayleigh criterion. So Rayleigh did an experiment. So the thing is, maybe you have read it before in high school, that there is, if there's light coming through apertures, there is some limit on how small of a feature can you make. We call it resolution limit. Resolution limit is simply stated, it's the minimum resolvable feature, what is given here. Minimum resolvable feature, W min, and the formula is K1 lambda over NA. K1 is a constant, we call it lithographic factor. Lambda is the wavelength of light, right? And Na is numerical aperture, which is a feature of the optics. And its formula is N sine alpha, numerical aperture, where N is called index of medium and alpha is the half acceptance angle, the angle at which the light can travel through a lens. Just stay with me that this is the formula that you have to know. That minimum feature is W min, and that's K1 lambda over NA, right? K1 is the lithographic factor, which is 0.75 for photoresist. Numerical aperture is a function of index of medium and the angle. Now, in this relationship, if I want to make things smaller, right? Nanotechnology, you want to make things smaller. What do? K1 is constant, Na is constant. The only thing we can do is I can make lambda smaller, wavelength smaller, right? We are talking optical lithography. So we are dealing with the wavelength of light. To make smaller feature, I have to bring down either lambda down or I can take numerical aperture up. This relationship here, right? With me on this? Seems straightforward, easy to do. You can bring the wavelength down and we can make smaller things. That's called resolution limit. Now, there's another thing which is called depth of focus. Now, depth of focus is there anybody photographer in our class who likes to do photography?
No, but from what I recall from the photographers I did speak to, just how far away you want to, the distance of where you want the camera to focus.
Right. So basically the idea is, they make sometimes they make interesting pictures where they take a picture of the cup and cup is in focus and everything is out of focus at the back. Gives it artistic touch. I think now the iPhone has that feature also in portrait. You take your picture and everything else is kind of out of focus and only you are in focus. So that's kind of small depth of focus. They want to just focus at one plane and everything else they want to be out of focus. Or like Edgar is saying, that you want to have many different levels in focus, then you have to have a bigger depth of focus. So depth of focus is the concept where you want to have different levels in focus. And why it's important? Because we are dealing with light here. When I'm exposing a wafer, I want to have my surface where I may have features up and down. I want all of them to be exposed in one go. That's what it says. What is depth of focus? It's the tolerance, placement of Hold on, there's too much bars on my screen. So tolerance of placement of the image plane, that's with respect to lens. So basically we want to, I made this picture here. So if my wafer is, this is my wafer, and I have coated this with photoresist, right? So which it says PR on the top. When I shine the light, I want the shine to be in focus at different levels. I want it to be focused here. I want to be focused here. So I can, if there are maybe a transistor made which has its connection at some place, I want to cover that. I want to cover different heights on my surface of my chip. Remember I showed you picture of multi-level devices last time? So we have different layers. Depth of focus is where I want to have all those layers in focus. And that has a simple relationship, which is called this guy. So this is, what is this? Sigma? K2 lambda over NA square. So these are the same thing. Lambda is the wavelength, N is numerical aperture. So K2 is what is called constant for specific process. It's equal to 1. So previously we said, okay, if you want to make a feature size smaller and smaller, we can bring the lambda down, right? But here I say, if I bring my lambda down, my depth of focus also becomes smaller. I want my depth of focus to be larger. But this means I cannot just bring my lambda down. So these are actual problems when you are designing a feature. So here's an example. If you have a lambda of say 248 nanometer for a UV light, we can calculate exactly what is the smallest feature size we can make and what are different heights of features we can have on the surface of a wafer. So that's what I'm getting here is that, yeah, lithography, making things smaller is not such a straightforward thing. There are many things that are involved into that. Now, if I were to look at making billions of chips, billions of transistors, for example, on my wafer, there's another factor that comes in, which is called pitch. How close can I make those things close to each other? And that has another relationship, which is lambda over 2n times NA. So here again, if you are making lambda small, we can make pitch smaller as well. But again, depth of focus will become a challenge. Well, let's stop at this point, because what we will do is, and I'll post on Thursday, I'll post a lecture on what are the challenges when you have these issues. You cannot make things smaller unless you have a trade-off. And this picture, this shows this trade-off. You want to make things smaller, but there's problem that if you make pattern size smaller going this way, the depth of focus, they call defocusing level, also becomes smaller, which means there is a trade-off of how small can I make and how different levels can be exposed in one step. So we'll look at some more examples of this as we go forward. Let's see. Questions? All right. So
yeah. I had a question, but not associated with this, but not of the topics. Everything was very well understood. When you brought up the gold disc, the
wafer.
Yes, the gold wafer.
Wafer.
So I noticed while I was looking up for research topics that nano gold is becoming the new gold rush, if so to put it. Uh, how is that coming to be, or what is it exactly that's more attractive than what's been used?
So that nano gold or there's so many metals where we are getting nanoscale of those things. So basically, instead of having a solid, we are making particles of those things, very, very, very fine grains of those things. Now, those grains can be suspended in solution and they would never settle down because they're so small, the gravity has no effect on them. Where do we use those nanoparticles? They have many applications, not just as additives to change the features of something where we add them, for example, paint, maybe, or for example, sunscreen. You know, sunscreen has alumina nanoparticles. You know, aluminum, right? Aluminum is a metal, but when you make, sorry, not alumina, titanium. Titanium is a expensive metal, right? But when you make titanium oxide nanoparticles, they have anti-UV properties. Sunscreen. Why do we, when you buy a sunscreen tube, what are we looking for? What is that? SDF rating?
Yes,
Well,
SPM.
basically, what wavelengths does it protect you from? So they have titanium nanoparticles, titanium dioxide nanoparticles. Similar way, gold nanoparticles, there's so many usages where they're using gold nanoparticles as well. So, or they call nano gold, or they use these things, different names of basically same thing. Maybe to change properties of other things where they want to add them to maybe have better adhesion quality, maybe better shine. I don't know what different applications have different kind of uses for those things. So it's not just metallic things. They are working with lots of carbon-based materials also, lots of organic things also, where they're playing with their properties at nanoscale. What we are talking here today is we are talking about devices. We haven't got into nanomaterials yet. We'll get there. Nanomaterials. Nanomaterials is things which are nanoscale things. Right now we're talking about devices that are made at nanoscale. Ultimately, this will, once we have some good idea on light, lithography, how light interacts and how can we make features smaller, we'll get into solution-based synthesis also. All right, so the cap today's lecture, there's history. UV light's been started using for a long time ago. 405 nanometer. Now I hope you can connect why wavelength is important here. We have been pushing things down by changing different lengths. 436 nanometer. So here are the wavelengths given. With the shorter wavelengths, we are pushing down the minimum feature size with other trade-offs. So this is giving us, we had G-line lithography, they're just given names. And then you have deep UV lithography, extreme UV lithography, which are based off of these wavelengths. And then it's a straightforward thing to find